Hello, welcome. This is my first video. I'm going to be proving using the epsilon delta definition of continuity. This is a real analysis problem. It's real analysis. Another name for this subject is advanced calculus, and I'm going to show you how to prove that 1 over x squared is discontinuous at x equals 0. Okay, it's just kind of we know the limit exists at x equals 0 for that function, but there is still a point of discontinuity, and this is how we can prove that that's true. Okay, so we want to say that the function of x equals 1 over x squared, and we're going to let x equal 0. We're saying prove the function x is discontinuous, and we're going to say at x equals 0, okay? And this is how we prove that. Because you would think the limit exists, but does the function value actually exist? Does the limit value actually equal the function? This is how we prove something like this, okay? Okay, so what we're going to do is we're going to say that, using the epsilon delta definition of continuity, we know that this is true, okay? So we start out with 0 is less than x minus, let's say, a, which a is 0. We know that, because that's the limit. That's as x approaches a, which a being 0, we know that we can prove that. Like that. So we use this definition because we know this is true. And we know that if there is some function of x, okay, so we know that we have some kind of function of x, okay, we know this is going to be greater than epsilon, okay? So if we have some d related to epsilon based on the choice of x, we have the function of x is greater than epsilon, okay? Because we know for some d, we know that for some delta that we have some epsilon, but that function of x, if we have some delta small enough to contain the limit 0, okay, so x approaches 0, so we know there's some delta that x minus a is restricted by, we know that the function x is going to continue without bound. So this is how we prove that this is not continuous, though, at that point. Okay, so we're going to take that value, take the function of x is greater than epsilon. So now we can write, we know that a is going to be 0. So we know that we're going to have x minus 0 is less than delta, okay? So we can just say 0 is less than x is less than delta, okay? That's how we put that. So we know that these are the conditions. So we want to put if 0 is less than x is less than delta, then the function of x continues without bound. It is greater than epsilon, okay? So, with that being said, we want to take the function of x and show that this function, dependent on x, is greater than epsilon, okay? Now, we're going to solve for x. So we want to take 1 over epsilon, and we want to change the sign, okay? 1 over epsilon, okay? Since epsilon is less than this, 1 over epsilon is now going to be greater than x squared when we reciprocate them, okay? So we have to switch the signs. But we can also write it like this. We can say x squared is less than 1 over epsilon. We can write it either way, but we know the sign has to change, okay? So now we know 1 over the square root of epsilon is greater than x squared, okay? So we know that's true. 1 over the square root of epsilon is greater than x squared. Or x, I'm sorry, x, which, like that, yeah. So now we know what x is. So if we take this condition is less than d, like that, we go back to this condition. Okay, when we replace that, we know we can make x equal the square root of epsilon like that. So we pick an x that's the square root of epsilon, okay? That's how we do that. So, then it's not x, it's d, sorry. So we want to show that x, because x is less than the square root of epsilon, this x, we know that d is equal to 1 over the square root of epsilon. Okay, we can replace d with the square root of epsilon. So now we have x is less than the square root of epsilon. And we know that this tolerance of d contains x. So that 0, that limit, is inside the tolerance of d, and yet x is less than 1 over the square root of epsilon. So now when we solve, we can take 1 over x is now greater than the square root of epsilon. Okay, because we have to change the sign. We're reciprocating both sides of the equation. The square root of x is greater than the square root of epsilon. 1 over x is greater than the square root of epsilon, and therefore 1 over x is greater than epsilon. Okay? So that, using d, we know when 0, the limit, as we approach the limit inside of the tolerance of d, that 1 over x squared, the function, goes outside of the tolerance of epsilon. And because this function, we know that we've proven that the function of x is outside the tolerance of epsilon, the definition fails. It fails because function of x has to be within the bounds of epsilon. If we take the function of x and we take some limit like this, we have to have that inside the value of epsilon. So that limit exists, but it's outside the bounds of epsilon. So it's actually that the limit exists, but the function does not. Okay? The function does not exist. And I'm sorry, I wrote that wrong. It's supposed to be the function of x minus L is greater than epsilon. So if we actually solve for the function of x would be outside of this. Okay? It would be outside of this. So it would not be equal to the limit. Okay? Since epsilon is only so big, epsilon is not a finite. Epsilon cannot be finite, so its tolerance cannot be finite, and the e has to be greater than 0, and epsilon also has to be finite to capture or keep the function of x within its bounds. And it is just not. Okay, function of x exceeds the tolerance of epsilon. So we have proven, with all of this, that the function of 1 over x squared as x approaches 0 is, in fact, not continuous. Thank you.